Next presenter is Adam Smirowski from CGG.
Before starting, I just wanted to address some false information from Monday's plenary session. Firstly, CGG is not bankrupt. CGG is going through a court-approved financial restructuring process and continues business as usual. Secondly, it was incorrectly stated that CGG Airborne is for sale, when in fact, CGG Airborne and Multiphysics are core parts of the CGG offering. The truth of the matter is that CGG continues to invest in and develop improvements to its airborne technology, and this is the focus of my presentation. I'm going to be looking in particular at innovations on the airborne EM side. Over the past 5 years, we've had a few different innovations with the overall goal being to increase bandwidth. Secondly, I'm going to look at MultiPulse, which is two different excitations within the same waveform with the goal of improving near-surface resolution. First, I'm going to look at trying to get better depth of exploration by decreasing the base frequency. And this is through a redesign of the receiver suspension on Helitem and on Tempest. Low base frequency has been the goal for a number of years, both in Exploration 97 and 07. Authors described the utility and the difficulty of obtaining low base frequency measurements on an airborne platform. The main challenge is the high noise caused by the coil motion, as well as increased noise due to less chance for stacking on the low base frequency. So in order to accomplish reducing that coil motion noise, we've had a redesign on both the Helitem helicopter system and the fixed wing Tempest system. And there's some boring patent figures down here. So we required a different solution for both of those platforms. The end result is that we have greatly decreased coil motion noise and the resonant frequency of the suspension. And on the Helitem, we have a redesigned coil, which has greatly reduced electronic noise and partially offsets that reduced chance for stacking. This shows the high altitude receiver power spectra. What's important to note, we're most interested in the low frequency, is that where the noise floor is met occurs at a lower frequency. Sorry, the blue curve is for the new suspension system. The black curves are for the old suspension system. So we've decreased the frequency at which the noise floor is met. So this is why we can operate at lower base frequencies with no motion noise penalty. And there's a drastic decrease on the Tempest side. But both are now well below the 12.5, 15 hertz level, and in fact below 10 hertz. So why do low base frequency? There's two reasons. We want to increase the measurement time for exploration in conductive areas. Also, according to the Liu waveform factor, a wider pulse preferentially energizes stronger conductors. So we want to allow room for this wide pulse. If you maintain, say, a 30 hertz system with a wide pulse, you'd have a pretty limited measurement time. So we want to maintain that long measurement time for exploring in conductive areas. And this is just an example from Exploration 97 showing the effective pulse width. So it's the same sort of power and everything, but the narrow pulse has a large response from the overburden, whereas a wider pulse preferentially energizes stronger targets. So we have a field test where we had different pulse widths on the 30 hertz and 15 hertz side. And I'm just going to show a 4 millisecond pulse with a 30 hertz base frequency and an 8 millisecond with a 15 hertz base frequency. This is not an ideal test for the low base frequency, but it is useful for showing the effect of pulse width. And it's still useful in showing that there's no large increase in the motion noise for the 15 hertz system. We have flown this on commercial surveys where we get very good results, but unfortunately we couldn't get permission to show that here. Just going to skip through this one. This is the 4 millisecond case. We have the early, this is an amplitude grid, the early grids on the right and the late grids on the left. So this is all overburden response. And then when we get to the late time, where late time here is only 2.5 milliseconds, we start to see the conductive targets of interest. This is the 15 hertz, 8 millisecond pulse. We see a somewhat similar overburden, but as we go to the later times, we have a very different response here. So that wide pulse is much better at energizing and leading to a response from those targets at depth. Moving on to the MultiPulse, where the goal is to improve near-surface resolution and sensitivity to resistive targets. The goal is to get more high-frequency energy. And what is MultiPulse? We're generating 2 different excitations within the same waveform. And this is within one waveform, so we get 100% ground coverage with both excitations. The square pulse has a much sharper DIDT, so it has more high frequency energy in it. And this slide just shows the transmitter power spectra. Red is for the half sign alone, and you can see that when you have MultiPulse filling in with this little square, you fill in the null, as well as getting more high frequency energy. So we found that this is really beneficial for resistive and near surface mapping. What's also useful is the square pulse has much smaller current, so it's much easier to turn off, and we're able to get a much earlier first skate, 8 microseconds instead of 50 microseconds. So that's helping with that near surface information as well. We're also maintaining the low frequency energy into the ground. This slide shows the geobandwidth of each of the pulses. So geobandwidth is the response from, in this case, a wire loop target. The blue curve is for the half sign, amplitude, and time constant. So we're interested in looking at the resistive end. For 2 similar channels, you can see a much larger amplitude from the square pulse. As well, we also have the benefit of this earlier first channel. So we're able to map weaker targets much better, while maintaining, and the half side provides us with that late time sensitivity to very strong conductors. And here's just a field example from a gold exploration survey. We have an amplitude grid from the first square channel and from the first half sign channel. And you can see a lot more detail, much better resolution of features using that first square channel. And in fact, we can look at the 7th channel, the 8th channel from the square, and that shows pretty similar resolution to the first channel, the half sign. So by using MultiPulse, earlier channels, much better mapping capabilities. And this is just looking at the geologic bandwidth as a result of that. By adding in MultiPulse, we can increase our sort of resistivity aperture and better detect a wider range of geologic features. Thank you very much.
Adam was fast enough to allow time for questions.
The grid there was at nanotesla per second. Sorry, yeah, it was dBdt nanotesla per second.